All right, I think we could get started.
Right.
The number of the participants. That's good. Okay, well, thank you. Welcome, everyone. Akash Kharita is our new incoming grad students. Congratulations for first-year grad students to volunteer to present. It's an inspiration. Akash has done tremendous work already during his master thesis in India, and so Akash already has a few papers in, coming as a first-year student, so it's a great experience. And as you will see, so Akash is very enthusiastic about random forest algorithm, and I'm sure he will share that passion with you today. So we have extensive discussion about why random forests are good. But it's been really a great pleasure with Akash, and we're editing our first paper from like summer work on ice quakes and earthquakes in Alaska. But I think Akash today you wanted to show like overall what in seismology we've been using random forests for. And so anyway, take it away.
Thank you, Maureen, for the introduction. And I will introduce myself once again. I'm Akash Kharita. I'm a first-year PhD student, and I'm working with Marine Dinor. And currently, my topic is focused on detection, classification, and characterization of near-surface events. So, for example, landslides, rock falls, and the region I'm concentrating on currently is Mount St. Helens and Mount Rainier. So, I'm building systems for clustering of surfaces that are occurring in that region. And previously, like Marine said, I have done some work that involves random forests. And during that work, I was doing some literature review, and I came to know several exciting applications of random forests in seismology. So, for example, automatic forecasting of volcanic eruptions, geothermal eruptions, earthquake early warning systems, GPS displacement and seismic data relationship, automatic surface event detections, and automatic quality control. So there are so many exciting applications. And although it's not possible for me to cover all those applications in this short lecture, but I would like to point out some prominent applications. So I will give a very brief introduction to random forests, as my current talk is mostly focused on the applications. But essentially at its core, random forest is composed of decision trees. So we use a lot of decision trees in our daily life. So here is one particular example of decision tree. So decision tree is basically, we want to determine something. So we ask a question, for example, is the person fit? And then based on that question, we define certain set of decision rules, and based on some yes or no, based on the result of those decision rules, we try to determine whether a person belongs to a given class or not. As a seismologist, we also use decision trees. So whether we look at the seismogram, we try to determine whether it's from earthquake, whether it's from explosion, whether it's from surface events or not. So scientifically, there are some, yes. Oh, yeah. Oh, sorry.
Can go to the left side.
Left side.
Yes.
Yeah, so scientifically, there are certain terminology that's used for decision tree. So the first is called decision node, where we have a condition, and then based on that condition, we define certain set of rules, and based on that rules, we try to classify the objects into something. Now, decision trees individually, when we try to apply it to seismic problems, they tend to suffer from the problem of overfitting. So they are highly overfitted to a given data. And under such condition, when we show them new data, they tend to behave poorly. To solve this problem, we have a random forest. So random forests are basically ensemble of uncorrelated decision trees. So what I mean by uncorrelated decision trees is, since individual decision tree suffers from the problem of overfitting, if we define trees which are different in structure, which are trained on different subsets of data and different subsets of feature, and then combine their predictive power, that's called random forest. So it's the process when we use when we train the decision trees on individual different subsets. That process is called bagging. And when we resample our features and train those features and put those features into dysentery is called bootstrap resampling. So random forest is an ensemble of uncorrelated dysentries. Now, the way it works is we have, say, thousands of random dysentries in a given random forest model. Each of the dysentry is trained on a specific subset of training examples, and then it will give an output. And then the final output is the majority of the output. So the output that we get could be a label, could be a classification problem, or it could be a continuous output. So it could be a regression problem. So let's start with some of the application. The most prominent application is precursor recognition. And there was this paper that was released in 2020, automatic precursor recognition and real-time forecasting of sudden explosive volcanic eruptions. So this paper, the motivation behind this paper was during 2019, there is a white island or Wakari Island near the north of the New Zealand that erupted in 2019, December 9 December 2019. And that resulted in catastrophic loss of lives. Now, the current volcano monitoring system is done by the GNSS, which is a volcano monitoring agency of New Zealand, and it indicated the alert level equal to 2. So the current monitoring system is called volcanic alert level, and it allocated volcanic alert level equal to 2 on the morning of the eruption. That indicates it's basically moderate to heightened volcanic unrest, and it's safe for tourists. It's not an eruption. However, that system obviously failed, and as a result, the volcano monitoring agencies are criticized, and other scientists are criticized. And so there is a need of system that can detect any sort of volcanic eruption without major visible precursors. Now, the current volcanic alert level system is very heuristic. So it's basically determined by observing the gas measurements, the SO2 measurements, the temperature measurements, the real-time seismic amplitude measurements. However, not all volcanic activities show the increase in those kind of measurements. That's why the system failed. So scientists here, they try to, so this is how the typical RSAM looks like, on the basis of which the decision is taken, the well is allocated. So this is real-time seismic amplitude measurement. So basically what we do is we take a seismic data and we filter it between 2 to 4.5 hertz and take the modulus of it. And the colored region shows the individual eruptions for which the well was 3 or greater. Now you can see there are periods of heightened volcanic activities, but not all of them raised alert. These are the events which are also used in training and testing of this model. So the model is trained on the 4 of these events and tested on 1 event. So the colored region shows plus and minus 1 month, which is used as a testing interval. Now, how the model works. So the first series is a real-time seismic amplitude measurement. This is what's usually observed by the monitoring agency. Author also extracted 2 more different type of series, which is medium frequency band and high frequency band. And then they also extracted another type of series, which is called DSAR, which is displacement seismic amplitude ratio, which is the ratio of displacement in the medium frequency and high frequency band. All of these kind of series have previously proved to be important in volcano monitoring. And here we are seeing how they vary at least 3 or 4 days before the 9 December eruption. So there is, we can see some obvious precursors in the RSAM. However, it was not enough to raise well to 3. So, and then here is their model's output. So here is the final output of the model. and it can clearly show that there is going to be an eruption at least 1 day before. Now, after they extract this kind of series, they defined windows, 2 days windows, and each window was labeled whether there is going to be an eruption or not eruption in the next 2 days. So for example, if there is an eruption in the next 2 days, this window is going to be labeled as eruption. And if there is no eruption, it's going to be labeled as noise. And then there is a sliding window, and it's sliding by 12 hours. So basically, windows like this are defined on a continuous data, and from each continuous data, it's converted into these 3 or 4 types of series. And from each series, 700, 800 features are extracted using standard machine learning feature extraction process. And and then the random forest model is trained. So here is a step-by-step methodology. Now, the main challenge they face is we just have 5 eruptions, but we have a lot of noise data. So for example, in total, we have 16 eruption samples based on the classes, based on the individual windows, but we have more than 9,000 noise windows. So they suffer from a huge problem of data imbalance. So let's see how they tackle this. So for example, this is their data. Orange windows are the eruption windows, and the green ones are the noise windows. So they split this data into test and training. So they train their model on the 4 eruption, and they keep 1 eruption for testing. So 1 month interval for testing. Next, to maintain the data balance, they randomly subsample noise from the data, and noise sample, they keep it equal to the eruption sample. So for example, this subset, it contains almost equal level of noise and eruption sample. And they repeated this process 1,000 times such that in a given subset, we have an equal number of noise and equal number of eruption samples, but we have a different kind of noise in different subsets. So they did resampling without replacement. In this way, they covered around 3% of the noise, but still they were able to cover the problem of data imbalance. Now, on each subset, they trained a decision tree, optimized the decision tree based on whether it's an eruption or not, and they defined hundreds of decision trees. And then they input the test window, which corresponds to the eruption window. And from each decision tree, they ask whether it's eruption or not eruption. And based on how many, the fraction of the decision trees that voted it in the favor of eruption, they output a model forecasting threshold, forecasting output. And based on whether that forecasting output is above or below the threshold, they issue alert. So here is the final output of their model, and it raised alarms several times. So there are so many false positives. It was also able to detect 4 events, at least. Here you can see. So the green ones represent that there is an eruption during alert. And also it was able to miss 2 eruption events. So the goal here is to reduce the false alarms. So for example, the probability during when an alert is issued, it's around 20%. So the major challenge here in this paper is to increase that probability that whenever there is an alert, there is going to be an eruption. Now, the second thing to be noticed is it's good that it just missed 2 eruption, and the reason for that is it missed this 2013 eruption and the 2016 eruption. So the 2013 eruption was a peculiar event in which there is 3 successive events that occurred within short time interval, and also it showed anomalous signature. So the black series here represent the RSAM, and in this case, RSAM is more than medium frequency and high frequency. So that's why the model was not trained on this kind of event, and this event is particularly different from all kind of other eruption events. That's why this model, this eruption was missed. And it's one of the challenges that we have is the volcanic systems are very unpredictable. They have diverse styles of eruption. So a model has limitation that it can only recognize the events on which it's trained. So we need a proper training catalog, and we need a proper styles and classifications of eruption system. The 2016 eruption was missed because it didn't show any precursory activity at all. So all the background noise, all the other kind of series were at the normal noise level, and it erupted very suddenly. So that was one paper that discusses precursor recognition. And here is another paper that's also based on precursor recursion, but in a different geological setting. It's based on forecasting of the cold water CO2 geyser. There's a geyser in New Mexico, and it erupts every 17 to 23 hours. And near that geyser, there is a seismometer, there is a temperature sensor. And also, the main problem here is to identify eruption signals and precursory signals and differentiate it from the anthropogenic noise. So this area is heavily influenced by anthropogenic noise. There is a crop activity, there is a traffic activity. And as you can see in this signal, in this subplot, the eruption is nearly invisible compared to the other kind of anthropogenic activity. So the goal here is to determine when there is going to be an eruption. So the first plot again shows the eruption activity, and there is other sort of anthropogenic noise. And here is the zoomed out plot. So what I like about this study is something that they did in the data processing part that enhance the eruption signals and suppress the background noise. So it's an interesting application of denoising as well. So what they did is, so here's the zoom out plot, and it shows daily temperature variation. So it's obviously located near geyser. So around 6 a.m. temperature is cold, temperature is minimum. So it shows the maximum amplitude. So here is the bandpass filter series. So the bandpass the data by 0.1 hertz, and it's the normal series. And now is the interesting part. So what they did here is they defined a model which is called autoregression model. So autoregression model predicts the next value based on a certain value from the past. So they trained the autoregression model using some initial data, and then they subtracted the autoregression model's output from the initial data. This resulted in the noise being eliminated and the eruption and precursory signals being enhanced. It's because the noise is very predictable. The noise is happening, the same kind of noise is happening during a regular intervals. So the autoregression model was able to predict the noise very well. However, the eruption is not so regular, and the precursor signals are not so frequent. So it was not able to predict those kind of signals. So when you subtract this series from that series, the precursors and the eruption signals seem to be enhanced, and the background noise is suppressed. So, and then they train the random forest model and classify this. I don't have a plot for performance, but they performed very well. So that was all about the precursors. Now we are going to see some other important application, which is event detection. And this particular paper caught my eye. It says machine learning improves debris flow warning. It's based on a setting in Illgraben. Illgraben is this area, Illgraben catchment, and it's frequently suffered by a heavy debris flow. Here is the channel from which the debris flows occur. And in 1961, there was a huge debris flow that resulted in the disruption of highway, and that resulted in the blockage of highway. So in response to that, Swiss monitoring agency installed some check dams that control the speed of debris flow, some 30 check dams along this path. So the CD1 represent the first check dam, and the CD29 represent the 29th check dam. So currently this debris flow is monitoring using the instruments which are located inside the channel, and the warning time range from 5 to 10 minutes. And the major drawback of the current monitoring system is it's not able to determine if the debris flow in the upper part of the region. So the goal here is to use the data from the seismograms and develop a monitoring system which will automatically detect the debris flow and also provide the warning. So here is a snapshot from check dam 29, where there is a video camera that's installed, and that activates whenever there is a debris flow. And here is how the typical seismograms of the events look like. This is from IL 12 seismogram. So here is how the typical debris flow seismograms look like. So they are emergent in nature, and they have a frequency range from 0 to 50 hertz. And you cannot identify different P and S phase. And here there is also a signature of thunder. So now what they did here is they divided, so they took the seismic series from each of the station, and they divided each seismic series into 100 seconds and labeled that series as a pre-CD1, post-CD1, and noise, based on whether the debris flow is before CD1, after CD1, or the noise. So for each event, they define the start time as the earliest arrival in the seismic signal, and they define the end time as the latest time that was noted for the signal in the last station. So based on that, they divided each continuous seismogram from each of the station into 100-second window, and then they trained their model on that. And this represent pre-CD1, this represent post-CD1 at IL number 12. So after that, from each of the in the testing data set, they predicted the label of each of the seismic series from each of the seismic station, and then they choose the majority vote, the majority label that was provided by majority of the stations. So here is their performance. So they were able to determine around 13 events. All of these 13 events are independently confirmed by the local agency. In addition to that, they are able to determine some additional events which are not previously observed, and which were later confirmed by the agency. And here is the another method that was defined by the same group. And comparison to that, this method detects more events. Here, this plot represents most important features. So it's particularly interesting to note what are the most important features. So the features, the most important features they found are the network-based features. So first feature is the ratio amplitude. So the ratio of RMS amplitude, maximum and minimum, maximum amplitude and minimum amplitude across the station. And then they also the second most important feature was the station number with the maximum amplitude. And the third most important feature is the maximum cross correlation that was observed between the stations. So it's all network-based features. So it emphasizes that for a monitoring, for a flow system, we need to extract network-based features. And here is their performance. So most of the confusion that was occurring was most of the pre-CD1 was labeled as noise, and most of the post-CD1 was labeled as pre-CD1. So that's the major confusion. But otherwise, the results look like more than 90% accuracy. So it performs really well. So the way it works is, as soon as the window is labeled as pre-CD1, after two subsequent detection, an alarm is raised. It says that there is something that goes on pre-CD1. And after 10 subsequent detection of post CD1, and final alarm is raised, and this number is chosen as to reduce the false positives. So there is a time lag. For example, the time lag between the initial detection and the alarm raise is 2 minutes, and for this case it's around 16 to 18 minutes. But compared to when the flow arrives at CD1, and when the first monitoring, compared to the previous monitoring times, that's based on the local instruments that are deployed by the Swiss agency, this model provide enhanced warning times as much as 3 hours for certain events. And here is some new detection event. So this event was not detected previously by any agency, and it was later confirmed as actual debris flow event. So this model is also able to detect new events. Now, they also tried to do something that I'm particularly interested in, is they tried to determine the size of the debris flow based on the seismograms. However, they could not find very good relation between volume and the amplitudes recorded at individual station. However, there are some sort of correlation that was observed between average amplitude impact force spectra and the RMS. But these are observed for one or two particular cases. This cannot be generalized. So this is still a area of research they are working on, like how to determine the flow parameters from seismograms. And they are also working on the transferability of this model. So this was a very quiet area, very well monitored area. If they want to extend this model to other particular setting, what changes they need to make? So here is another interesting application. Random forest can also be used to determine the relationship between two kind of series. And this particular paper is the one that catches my eye. Here, what they did essentially is they derived the GPS series using seismic data. So the background of this research is here is a GPS station, here is a seismic station, and it's based on the observation that the energy released during slow slip computed using GPS measurement is found to be much more compared to the energy released computed using seismograms. So why is that? They were trying to figure out this mystery, and what they found is if they extract the features from specific windows, if they extract features from seismograms and then they try to plot the correlation between the features and the GPS series, they found that there are some features that show very good correlation, and this is their output regression using the seismic series. So the red one is the observation, and the blue one is the model output. And you can see they fit very well. And so it shows that we can essentially derive the slow slip or the GPS series using the seismic data. And here is the model versus observation of the GPS output that was predicted by the model and the observed GPS displacement rates. So what they found is one particular feature, which is 60 to 70, which is around, which is a 40 to 60% quartile, which basically means you plot a distribution of amplitudes from a seismic window, and then you compute the amplitude where below which 60% of your information is below which 60% of distribution is there, and you compute the amplitude where below which you have a 40% distribution, and then you subtract that. So that particular feature tends to provide a very good prediction of the GPS slow slip rate. So in the black is that feature that is extracted from the seismogram, and in the red there's that feature that's GPS displacement series.
This is directly just a feature.
Yes, that's directly just the feature. Yeah. And so you can see they just correlate really well. And it could be because this is controlled by physics, or it could merely be a coincidence. However, this suggests that it's this feature is in particular controlled by physics, and the tremors, the slow slip, continuously produce seismic output instead of a small burst of energy as previously thought. That's what their main conclusion is. Here is the plot of the particular feature, and on the y-axis is the GPS displacement slip rate. So here they smooth the time series using 60-day average, and here they smooth the time series using 1 hour average. So this kind of correlation is only observed when the seismic series is smoothed, and which also makes sense because smoothing will reduce the noise. But this is the main discovery of their paper, that you can derive GPS series using just seismograms or seismic features. And this also has triggered other kind of studies, for example, deriving the correlation between rainfall, between temperature and other sort of near surface investigations. And fourth is this is the one of the most common application of random forest, and it's one of the area I'm working in. This particular paper caught my eye because it used multi-station and multi-classes. So normally the models that we define are based on one station, but this particular study uses multiple stations, and this system is currently operational as far as 2017. It was written in the paper that it's currently operational. And so what it is, there is a volcano near Madagascar, La Reunion. It's called Pito de la Fournaise volcano. And so this particular inset represent the volcanic crater and volcanic summit. And there is a network of short period and broadband seismometers. So the authors consider 4 kind of stations. So 2 of them are located on the summit, 1 is located inside the crater, and 1 is located far away from the volcano. So what they did is they have these 8 classes of events, and they are trying to build an automatic classification system. These 8 classes are shown for 4 different stations. So this one is for the station which was located away from the volcano, and this one is for the station which are located at the summit. This one is for the station which is located inside the crater, and this one is for the station located again at the summit. So summit volcano tectonic event and deep volcano tectonic event, it's basically all sort of earthquakes that are happening, or the volcano tectonic events that are happening inside the volcano, but based on whether they are above sea level or below sea level. So these are it's really hard to differentiate between them, but these are the events they used in their training. And the catalog of these events are developed by the members at OVPF, which is the volcano monitoring agency responsible for monitoring this volcano. And there are local events. Local events are all the earthquakes which are located in 10 kilometer within 10 kilometer of the island. So you can see there is a distinct P and S arrivals, and there's a difference of 0.5 seconds. And then there are regional events. There's a T phase. I still don't understand what this is, but this is one of the classes there. And there's teleseismic events. There's rock falls, which happen, which occur a lot at this volcano. And there is a sound wave, which is also an interesting class. But this volcano is frequented by heavy thunderstorms. So these are different kind of recordings, and their goal was to build a reliable automatic classification system that will reliably predict the given event into one of these classes. So here is what they did. So they initially built the single station monitoring system. So initially what they did is they have an event catalog, and from each event they extract 40 features. And so this is essentially what we input in our model. So we have classes, class labels, and we have corresponding features. And from each feature, from each station, they select the top 10 best features. And best features are chosen based on the importance in determining the class of the signal. And then they select 4 stations, and they combine the best features predicted from each station, and they redo the analysis. And then they select 10 best features again, and then they finally use these features to predict the class of the event. Now, compared to the single station, so they also perform the single station. So you can see the accuracy rate is around 70, 80, maximum 87% for the station which is inside the crater. Compared to this, we have a better accuracy for the 3 station combination. So they also implemented 4 station combination, 5 station combination, but they found that 3 station combination provides the maximum results. And there is a considerable confusion between summit and deep events. So you can see there is a black sort of sign. So this represents confusion. But the main outcome is the multiple stations provide good accuracies, and their system works. So you can see the accuracies are around 93%, which is reasonable for given that it's automatically able to classify events into so many classes. And it's particularly interesting to note what features matter the most at different stations. So for the station which is inside the crater, duration matters a lot. For the station which is away from the volcanic crater, we have a duration over amplitude. So it's also important that at some stations, distance affect, propagation affect, control what features are important. And so based on the location of the station, different features are found to be important. And what factors control what kind of features, it's still one of my other research interests. So for the station which are located near volcano, we have a spectral features and the energy-based features that are most important. For the station which we have, which are away from the volcano, we have more temporal-based features that are important. Thank you. Yes.
Just a question about the features. Is that you have a whole suite of features? Is that something that the person designing the experiment selects? I'm going to use 40 features, or
yes,
is that something that, how do you pick those features?
Okay, so the question is, how do we pick the features? Okay, so the problem with feature selection is we want to have as minimum features as possible, because if we include more features, it affects the performance of the machine learning model because of the curse of the dimensionality. So we only want to select most important, most discriminatory features. Now, some studies, they choose features based on their experience. So experts typically know what characteristics they see while classifying whether the event is earthquake or it's a man-made explosion. So for in that case, we see polarity, we see P and S arrivals or P and S difference or things like that. So sometimes it's based on the expert's experience. Sometimes it's just randomly extracted. So we extract 700, 800 features, and then we choose the most important feature. It's within the algorithm. So it's based on what features are selected most frequently at during the when the model is being trained, which feature is given most importance. So it's based on that. And there are other statistical tests that can determine the most important features. So that's how the features are selected, and then that's how it works. And certain at some times it's observed that the spectral features are the most important. In some studies, it's observed that the temporal based features are most important. However, it's still area of research for a given problem. What kind of features should we extract? So we don't have to go through the whole feature extraction process. So yeah, it's still an area of research. Yes, yes.
Yeah, so thank you very much. That was a really great overview of different applications.
Thank you.
Great. And I think what you're getting at, I think the fact that it is random forest approach, you can see which features really are important.
Yes.
Is what makes it attractive to old-fashioned seismologists like me, because I see what comes out and I'm like, yeah, that makes sense. This is what I see by eye. I think this is what I would have chosen. Right?
Yes.
So that's I think why it's nice, but it's much more efficient. You can explore the feature space much more widely.
That's right.
Um,
Yes.
so it's
Yes. And to add more to that, so scientists or in particular studies, they always explore multiple models. So they use SVM and other sort of machine learning models that are available, and random forest always outperforms them. It's and there's a official study that's done on a lot more data set and lot more generalized data set, that random forest outperform most other sort of machine learning. And there's still a debate like which performs better, random forest or neural network. I prefer random forest because it's easy to interpret. It's not a black box. You can easily see the features, you can control the features, and you can define the threshold. And you can get the feature importance from other machine learning techniques as well. However, they are more like a black box. So that's why random forest is being more popular. Yes, yes, yes.
In the random forest, is there a way to build in some a priori information? So for example, if it's an earthquake and you have an array, there are only certain sensible move out. Things can only come in a certain order. Is there a way to build that kind of information into the algorithm to help guide it and it would limit the number of, could that be part of the decision tree or something?
Could be as a TS minus TP feature. It would have to be put in as an input feature or something, because like the neural network that sees the temporal resolution, these features do not see much of that temporal, the phase. They don't see the phase. It's statistical properties to the like histogram, the mean and everything.
You can't really combine it with any sort of a priori knowledge.
Actually, yeah, no, I think you could if you parameterize TS around the pics. The pics are part of the data sometimes, so I think that could be parameterized.
I still don't understand the question. Can you
Oh,
explain?
when you have obvious move-outs of waves in the seismogram, can that be part of the
Or,
actually knowledge?
and that's
Or
just
like-
an example of some a priori knowledge and how the system works. Can you build that to limit the number of cases or number of possibilities? Seems like it would help.
Like you using those information as input features. So like, for example, like you want to say how you can constrain your classification result using a priori information. Yes, that information can be definitely extracted as features. So scientists have extracted polarity based features or network based features. So I think that's possible.
There's another, there's paper that came out about combining these features with a neural network together to predict the effect between explosion and earthquakes. In Hong at the, I think the Lawrence, so we can do both of that time, the understanding the seismogram and the future space and together predicting. 90% is pretty good, no? Already, like, you don't
Yeah,
need that in
yeah.
your knowledge, it's
And it's indirectly in the physics, right?
Yeah.
The way they train, for example, the one feature in the last one that we discussed, where this farther wave station, it's the duration of the amplitude.
Yes.
and How far basically. the humanity. So it's a little bit indirect, but yeah, like order of, station.
Yes, and sometimes the features are purely statistical. So like mean, maximum, they are not really physics based, but they indirectly capture the physics. So for example, centroid frequency or the spectral kurtosis or skewness, things like that, they are statistically extracted. But sometimes they just relate to the physics of the feature. And sometimes some scientist group, they have defined their own set of features. So for example, this particular group, they define certain features based on their experience. So they have this particular script that runs in each of their research. So that's more like physics-based features. So my personal opinion is we should explore all sort of features, and there should be some sort of generalized knowledge, like which kind of feature to use in which case, whether it's a classification problem or regression problem, or yeah, that's one of the one of the problem that we face here. So, yeah. Sorry, what is a feature? Okay, okay, let me see. So the problem is, so you define, this is a seismic signal, right? And you define a window, say 100-second or 200-second. And in that 100-second window, you have raw seismic signal. That's, suppose if it's 200 hertz or 100 hertz, we have 10,000 samples in that particular window. Now, when we input this particular window into the model, it behaves poorly. And instead of this inputting raw seismic signal directly, if we extract features from this seismic signal, features can be mean of the signal, maximum of the signal, difference between P and S times, maximum amplitude, spectral energy, spectral kurtosis, lot of mathematical attributes that characterize the signal. So that's what feature is. So that reduces the dimensional space, and that captures the essential information that's essential for the classification. So for example, when when we look, if we are, as a seismologist, when we try to classify the signal into earthquake or explosion, we look for certain characteristic of the signal. For example, the frequency content in certain band or the polarity of the signal. So those are the characteristics. Those are the features that we input in the machine learning model. So there's the example.
It sounds like those are all features that you would predefine. So if you send this thing off to find its own features, you still have to do the combination of some features, or how would you just say find the features that are more important?
How the features are extracted? So sometimes it's certain scientists use the features from their own experience that they have previously used before in other sort of problems, and they know this would matter in the classification of this. So they define certain set of features. And there are machine learning packages that automatically extract features, statistical features, all sort of features. So you just have to input your data and they will automatically compute 700, 800 features. So those are statistical based features. But in comparison to the physics based features that are defined from the manual experience, they may or may not perform better. Yes, Alex.
800 standard features that might have the time series.
Yes.
And then you can give it some of your data, so it says, oh yeah, these features are probably most important in your difference.
Yes.
Like a principal component analysis. And how does it do?
How does it does? Okay, so there are various statistical methods. In case of random forest, the most simple method is what feature is chosen frequently for the classification in each node. So like what feature is chosen by the most of the decision trees at the topmost level. So here is the decision tree. So if you want to say, for example, this case, if you want to understand is the person fit, you want to ask it the most important question at the top. So is its age or less? So here it's the most important question. So based on in how many trees this particular feature appears at the top, the importance is computed in that way. Yes, Alex.
What if that first question is like, is the signal noise ratio greater than X?
Yeah.
If you have X equal, from 20 to 200, is that going to be 180 different features? Because that's not only like one type of feature, but it could be.
Is the signal to noise ratio greater or less than X?
And then also you could like calculate it in many different ways. So that's like one class of feature. And
yes, that's multiple features. I would say that's multiple features. So signal to noise ratio is one single feature based on a particular definition. If it's more or less than X, then you go to the next step and then you try to classify. So this at that particular stage, signal to noise ratio is behaving as one feature for one particular definition. If you use multiple definition, you extract, you use signal to noise ratio based on multiple definition as multiple features. You can totally use that, but I don't know if that will be helpful to your classification or not. And it would lead to a same problem of curse of dimensionality. It would unnecessarily increase the dimension of the features. So we want to keep only the most important features.
So, like, given a data set, could you, for example, find groups of features that are redundant to each other and find the best one in that particular one, so that you can you manually whittle down the number of features to find like the best type of signal noise ratio, the best type of spectral feature?
So that's a very good point that you raised. So features can be correlated. So for example, duration and there are other features, they can be highly correlated. and we want to find the best. So there are machine learning methods that are able to tell you which feature is the most relevant, even in that case, even when the highly correlated features. So there's a technique called recursive feature elimination. What it does is it will eliminate one feature and it will compute the result with the remaining features, and then it will eliminate the next feature, compute the result with the next with the remaining set of features, and based on that, based on the decrease or increase in improvement, it will rank each feature, and then you can get the you can select the top 10 best features. So you can there's a solution for that. So yeah, that's a good question. There are certain techniques that totally ignore the correlation between the features that are based on the normal kind of technique, which feature comes to the top node of each decision tree. So that do not consider if there are features that are going to be correlated or those features are redundant or not. So that's why certain papers, they use recursive feature elimination technique. It's a very time consuming. It's the only downfall. It's you are using each feature multiple times, so it involves heavy computation cost, but it will give you more accurate results.
All right, Akash is here for another 4 years, so.
Yeah, a lot of time. Yeah.
Great, thank you so much. That was great.
Okay.